Hey, welcome back, you crazy cats. Today we're going to talk about linear momentum in one dimension, specifically with collisions. You're going to learn about how to identify the different types of collisions, how momentum is going to be conserved through these collisions, what type of collisions conserve energy, and you're going to be able to calculate the initial and final momentums. Okay, let's start off with types of collisions. We have elastic collisions and inelastic collisions. In class, I'm going to talk about or show you marbles colliding, but an elastic collision is when things are going to bounce off each other. So I want you to imagine two marbles rolling into each other, or imagine two cue balls, pool balls rolling into each other. A basketball bouncing against the ground is an elastic collision. The other type of collision is an inelastic collision. An inelastic collision is when you have a collision and the two masses stick together. They may take off in a different direction, but what we have then is one mass after the collision. Whereas a basketball bouncing off the ground, you still have the ground's mass and the basketball. They're still two separate things. But imagine a bug on a windshield. The bug sticks to the windshield of the car, so you now have one mass. It doesn't change by much, but you don't have two separate masses. You now have just the bug-windshield combination. Okay, elastic versus inelastic collisions. In an elastic collision, what they want you to understand is that kinetic energy is conserved. In an inelastic collision, the kinetic energy is not going to be conserved. And we'll talk more about this as we've talked about as we introduce kinetic energy in our next chapter. But that's something to keep in consideration, is energy is not going to be conserved in an inelastic collision. A completely inelastic collision is where the objects stick together. So here's an example of where we have a mass coming from the heading north, and we have a mass heading to the east, and we have this collision. And afterwards, the two masses are stuck together here, but they're heading in the upper right-hand direction, or the northeast direction, at this new angle. The momentum of these two is still going to be equal to the momentum of what the two individually were. It's just now we have this one mass. Collisions may take place with the two objects approaching each other, or with one overtaking the other. So in the first collision, we have this big mass which is coming up on this smaller mass. It's traveling faster, so there's going to be a collision here. In this case, these two are traveling towards each other, so there's obviously going to be a collision here. Okay, with the conservation of momentum that we talked about, what we know is that the momentum before has to be equal to the momentum after. So whatever we had going before has to be equal to the momentum afterwards. So in this case up here, before we had a 10 kilogram ball rolling 3 meters per second, hits a 2 kilogram ball rolling 5 meters per second. And these probably should be worded the other way. The 2 kilogram ball is probably going to hit the other one. But what that tells us then is that before the collision we had 30 kilogram meters per second here. We had 10 kilogram meters per second worth of momentum here. So after, they tell us that the 10 kilogram ball rolls at 1 meter per second, and this 2 kilogram ball is now rolling at 15 meters per second. So we have 10 times 1 is 10 kilogram meters per second, 2 times 15 is 30 kilogram meters per second, for a total of 40 kilogram meters per second. So before the collision we had 40 kilogram meters per second of total momentum, and after the collision we still have 40 kilogram meters per second of total momentum. So one of the suggestions I would make is that you set up a before and after table. And what I mean here is before, talk about what the momentum of object 1 is. Talk about what the momentum of object 2 is before the collision. And then down here at the bottom you see me calculating it. And we add them up and we say there was a total of 24,000 kilogram meters per second of total momentum. After the collision, all right, we find out how much momentum object 1 has, how much momentum object 2 has, and they tell us that the car had 10,000 kilogram meters per second. So that tells us the momentum changed then from 15,000 to 10,000 here. It was originally 15,000, it's now changed to 10,000. The truck has 3,000 kilograms, but we don't know its speed. So what we can do is we can say beforehand we had 24,000 kilogram meters per second of total momentum. The car has 10,000 kilogram meters per second of that 24,000. So that leaves 14 1,000 kilogram meters per second left for the truck. So we can then plug that into our equation and find out what then is the velocity of the truck. And it turns out the velocity of the truck after the collision is 4.7 meters per second. Alright, so let's do a problem here. We have before and after. Before, the truck had a total momentum of 4 times 2,500 or 10,000 kilogram meters per second. The car has 3,000. So our total momentum here before the collision is 13,000. And they tell us it's an inelastic collision. So we want us to find out what is the velocity of the car and truck after the collision. Well, what we know then is that the total momentum is equal to the total mass times the velocity of the total mass. What happened in this inelastic collision is the two masses combine to become one mass. So I'm going to say that we have 13,000 here equals their total mass, which is 4,000, and solve for their velocity. I'm going to give you a few seconds here to pause it so that you can find that velocity on your own, and hopefully you got a velocity that was equal to 3.25 meters per second. All right, so this combined mass, the car and truck combined now because they're stuck together, are traveling 3.25 meters per second. So I've already did a lot of work on this one here. In this problem we have an elastic collision. So before the collision, the truck has negative 6,600 kilogram meters per second. I just haven't taken time to write the units in. The car has a momentum of 2,000 kilogram meters per second. So this car and truck are heading at each other. All right. As you can imagine, the total momentum after we add these two together is negative 4,600 kilogram meters per second. So after the collision then, we can find the velocity of the truck. The car afterwards, they're telling us, is 1,000 times negative 1, so it's negative 1,000. So we know that the total momentum is equal to the momentum of the truck I'm going to put TO for that. Momentum of the truck plus the momentum of the car, and we know that the total was negative 4,600. We don't know the momentum of the truck, but the car was negative 1,000. So that means the momentum of the truck after the collision is negative 3,600. So I can simply say that the momentum is the mass of the truck times the velocity of the truck, so we get negative 3,600 equals 2,200 times V. I advise you to pause it here and try to find out what that velocity is. Well, hopefully you paused it and found that the velocity is equal to 1.6 meters per second. Well, I'm going to kind of leave you with that. We're not going to go a whole lot more detail in our notes. Tomorrow we're going to be taking a look at this problem, and I want you to realize that right here we're starting to add some vectors into this. All right, we've been using vectors the whole time. They've just been easy because they've been heading right at each other. So now we're going to tell you that we have these new vectors that we're going to be using here with some angles. Well, hopefully that was informational. I'll catch you on the flip side.